Good time of the day. My name is Yulduz Khodjaeva, and I'm going to present my paper, Network Flow Entropy for Identifying Malicious Behaviors in DNS Tunnels. The research was encouraged by introduction of new DNS over HTTPS and DNS over TLS protocols in 2018. The idea behind DOH is to provide security and privacy by encrypting the data between DOH client and DOH-based DNS resolver. What seemed to be quite promising and effective solution at the start gained a lot of criticism later, with researchers claiming that DOH makes DNS tunnels harder to detect and analyze. Once the data gets encrypted, threat analysis based on plain text content of DNS queries becomes an obsolete tool for network security specialists. Host-based and network-based monitoring for DOH protocol was needed. In this research, we aim to explore the effect of entropy of a network flow to detect malicious behaviors in DOH tunnels. To the best of our knowledge, we are the first in terms of looking at flow entropy. The previous works have performed traffic analysis by calculating entropy at the packet level. By calculating the value of entropy of a flow, we augmented it with statistical features for identifying malicious DOH tunnels. Other than that, we explore above features using different machine learning algorithms in terms of complexity and performance. Lastly, we look at the minimum number of packets required to calculate entropy per traffic flow without decreasing the performance or increasing the complexity of our solution. Detection of attacks have become one of the most widely researched areas in a network security area. Scientists from the University of New Brunswick presented a two-layered approach to detect and characterize DOH traffic using time series classifiers. They classified traffic into DOH and non-DOH at the first layer and looked into DOH traffic itself at layer 2, separating benign behavior from malicious one. The authors of the paper extracted 28 statistical features from DOH traffic using DOH Laser tool developed by the researchers and fed them into a machine learning classifier. Random forest classifiers showed the best performance, with precision recall and F1 measure reaching almost 100% mark. The second studies explored the ability of self-organizing maps to detect DNS tunneling and exfiltration behaviors. Lastly, the author of the master's thesis used entropy characteristics of a network traffic in his exfil tool, a decision tree algorithm that looked at traffic state of encryption. The figure shows our overall research methodology that we applied. Three publicly available datasets are run through flow exporters, namely Argus, DOHlyzer, and Trendlyzer 2. For the entropy feature, four different scenarios are tested during the experiments. The first one does not deploy any entropy feature. The second one calculates an entropy value per flow by using all packets of a flow. The third one calculates an entropy value per flow by using the first 96 bytes of a packet's payload. And the last one calculates the entropy value using only the first n number of packets of a flow. For our research, we started from 6, decreasing the number n one by one. The final set of statistical and entropy features are fed into machine learning classifiers, including C4.5 decision tree, random forest, logistic regression, support vector machine, and naive Bayes. After the model is trained, 5 different testing datasets are used to evaluate the performance, complexity, computational cost of the trained models in terms of identifying benign and malicious flows. As it was mentioned above, we employed 3 publicly available datasets for our research. First dataset, called DOH was published by University of New Brunswick in 2020 and contains DOH non-DOH network traffic. A total of 33,000 DOH flows were used, half of them representing malicious and the other half benign behavior. Second dataset, Georgia Tech malware passive DNS daily feed, was released by Georgia Tech Information Security Center in 2015, and the capture continues up to these days. For our research, we used the pickup files for 2020 in the amount of 12,000 flows, and the last choice of dataset came to UNB publication again, now this time to CIC-IDS 2017 dataset, which contains both benign and malicious pickup files. For our research works, we were interested only in benign pickup files. A total of 12,000 flows were employed as well. In order to analyze encrypted DOH traffic, we augmented Entropy feature with statistical features derived from network traffic. Thus, no deep packet inspection was necessary. For feature extraction, we used three different flow exporters, Argus, DOHlyzer, and Trendlyzer2. Once we extracted three features from benign and malicious pickup files and made up a training model without an entropy, we looked at the results of classification. All three exporters demonstrated high performance, with Trendlyzer2 being the lowest one in terms of precision, recall, and F1 measure. However, if you look at the number of attributes used by decision tree classifier to separate attack behavior from benign one, we can see that Trendlyzer2 used the smallest number of attributes, 8, against 10 for Argus and 14 for DOHlyzer. Less number of features potentially enables simpler machine learning model and near real-time execution. Moreover, the ease of using Trendlyzer2 encouraged us to continue with this tool for further research activity. When it comes to entropy, we calculated the entropy feature in three different ways. Entropy is a measure of a state of randomness, disorder, or uncertainty. In this research, we stick to hypothesis that entropy characteristics of a network traffic could provide an accurate metric to show the randomness and therefore could be used to indicate the actual state of encryption in the flow analyzed. In the first case, we identify all the packets belonging to one flow and calculated the entropy feature of the merged packets payload. In the second one, we only considered 96 bytes, and in the third case, we started with n equal to 6 and went down one by one until we reached point of 4, when performance metrics were same as the entropy calculated over all packets of a flow. The bar chart on the right shows the average number of packets meshed per flow, and it is evident that DOH dataset is leading in terms of the metrics. On average, 31.45 packets are identified and merged into one before actually calculating the entropy value. As you might have understood, we used precision, recall, and F1 measure as our performance metrics. For the training and testing purposes, we employed VECA tool, an open source machine learning software used with the default parameters unless presented differently. The first tables on the left shows that the results of running training model without entropy feature. The training dataset show that F1 score of 95%, while CIC-IDS benign dataset hits a mark of 83%. Once we introduce the entropy feature, we see a significant increase for training and a couple of testing datasets. For DOH attack dataset, an F1 score of 90% gives a hint that most of malicious flows are misclassified as benign by our decision tree model. When we found an optimal number of packets needed for entropy calculation, which is 4, we run the same dataset with the same 14 features and notice that performance of classifier not only stays the same, but managed to perform better. In this case, we can say that we reached our objective of finding the minimum number of packets per flow that can provide a reasonable indication of the entropy of a flow without decreasing the performance of the classifier. The table presents a comparison of proposed model using C4.5 decision tree classifier against random forest, logistic regression, support vector machine, and naive Bayes classifiers. These four machine learning classifiers are chosen for further evaluations since they were used in previous works. It's interesting to see that random forest achieved the same high performance as decision tree, while the other three datasets failed to identify malicious flows successfully. Taking a closer look at the performance of random forest classifier, we start increasing the number of trees from 100 to 2000. It's evident that precision recall and F1 scores do not differ considerably. However, the tree depth goes from 24 to 26 as we increase the number of trees, which proves the higher complexity of random forest. Whereas the vector tool decision tree has a depth of 10, with the entropy feature being augmented with 13 statistical features. Once decision tree model is trained, 13 statistical features extracted by using Trainalyzer 2, and entropy value is calculated over first 4 packets, we can use it as our predictive model. By providing the new pickup files, going through the same steps, we provide 14 features into predictive models and get our expected labels. With the mounting criticism against DOH protocol, which can allow attackers to bypass organizational controls, new approaches to monitor encrypted DNS queries such as DOH are necessary. Heterogeneous aspects of datasets employed, starting from different protocols to different packet sizes, different flow characteristics, and different behaviors they capture, also indicate the generalizability of the proposed model over different real-life scenarios. Future research will explore the parameter sensitivity of the decision tree classifier for optimization purposes. The proposed system's behavior against evasive and adversarial attacks will also be analyzed to improve the overall robustness of the model. Moreover, predictive model will be evaluated on other datasets to investigate its generalization under concept shifts and drifts. The research has been made possible by Natural Science and Engineering Research Council of Canada Discovery Grant. I would also like to personally express my gratitude to Global Affairs Canada for studying Canada scholarship I was provided with. Thank you.